So just to give you a quick introduction to myself, my name is Christian Aparicio, and I will be moderating today's event. Thank you for being with us today as we go over random response analysis with our strength analysis software applications. With us to present is Micah Parks. Micah Parks is one of our senior application engineers here at MSC Software. He has been with MSC for over 17 years. He has a degree in mechanical engineering from the University of California, Irvine. And today he's here to share his thoughts on random response analysis, how you can leverage this in an engineering workflow. So the plan for today is he'll give a brief introduction and presentation over what random response analysis is. Then we'll do an actual demonstration of what the process looks like. And then if time permits, we'll have a question and answer where if you have any questions, you can submit those using the chat or QA window. And then we'll go ahead and answer some of those questions at the end of the presentation. So just to give you an introduction to what we do here at MSC Software, as I look at the participant list, I see that there are a lot of engineers on the call today. Many of you have to design certain components, hardware systems that handle various loading scenarios. That could be a gas turbine that's expected to run continuously for days or months at a time. You could be developing a launch vehicle where you have excessive vibrations you have to account for. If you're someone who's focused on a manufacturing process or a bottling process, one of your primary goals is to make sure none of the products tip over. And so with a lot of these scenarios, we all have the luxury of looking almost at the same engineering quantities, if you will. We're interested in things like displacements, accelerations, stiffness might be a very critical thing for you. We look at stress, so then strength is a very critical thing. Then we look at natural frequencies and so on and so on. What we do here at MSC Software, we develop software applications that can help you produce these engineering quantities. So if you're trying to model a launch vehicle or processing or a bottling process, you can use our software to do things such as motion analysis. There you can obtain things such as velocities and accelerations, determine what the motion or what the loading is of your dynamic system. We also have software applications that can perform a deformation and stress analysis, other software applications that can do heat transfer analysis, acoustic analysis, manufacturing analysis, and we can even do mechanical and various other types of analysis for composites at the micro level. So I know there's a lot we can go over today, but today we'll be going over something named random analysis. And then at this point, I'll hand it off to Micah Parks, who can then continue on with the call. And again, if you experience any visual issues, any audio disconnection issues, feel free to use the chat or QA window, and we'll be more than glad to help you during the call. And again, we will have a question and answer, so if you have any questions, again, use the question and answer window to ask, and we'll get to those towards the end of the presentation. And at this point, I think Micah, it's in your report.
Okay, thank you, Christian. So again, my name is Micah Parks, application engineer at MSC Software. Today's presentation is a little different than most. I have actually a collection of different software that we'll talk about. We'll talk about that part of it and, pardon the pun, but some other random topics that have come up over the last years or so that I think are good to put together into a presentation like this. So start off with a little bit of a different licensing scheme that we have available that might make it more plausible or more likely that you're going to end up with a couple of different pieces of software that will allow you to do random analysis. For the newer user, or maybe perhaps someone who doesn't do random analysis very often, talk a little bit about our comparisons between static and random analysis, and then a very, very short overview of what is random analysis, and that actually never ends up being very short, but I'll do my best to keep that in a reasonable time frame. And then, as Christian talked about, give a live demo, give you a little bit more feel for how you would walk through the process. The last section down there talking about the different types of software and what do you want to consider. There's a couple different ways to look at that, but again, this is a collection of different pieces of information. Another way to look at particularly this bottom section is these are kind of things that I would like to know about before I start doing a random analysis. It might sway me to use a particular solution or particular software, but it also might sway me the other way and go, well, look, there's actually some neat stuff over here. I might start off in one package and then actually transfer over to another one for doing random analysis. As far as the easy, medium, hard, it just depends. Once you get into setting up your model, or you have your model, you've gone through this, it's actually pretty easy to do random analysis. And those who know better usually consider it to be just a post-processing step, but you get some very good information from that. So that's what our agenda is. Let me go ahead and get going on this. So part of the reason to put all these things together is that we do a new licensing strategy called MSC1. If we talk about the MSC1 Starter Edition, so there's a special variation of MSC1 that does have cost advantages to it. This is a package where you would have Actran and MSC Nastran. Traditionally, it just depends on it really depends on your background. You might think of only using Nastran to do random analysis. That's fine. It definitely has that capability. Another variation on that is MSC.Random, which is a module inside of Actran. So this gives you the same general type of functionality, but arguably it's a lot easier to set up and work with. So that's a distinction. And again, you might actually end up hopping back and forth. So I can't go into obviously a lot of detail on it, but I give you some granularity on what situations you might consider using one or the other, and that is more towards the end of this presentation. The full-blown MSC1 package includes a number of different software. The addition to Actran and Nastran would be Actran. So Actran is for doing acoustic analysis, and it also has random analysis capability as well. And again, it may be a situation you would start off in MSC.Random, perhaps Nastran.Random, and then you might take your model and want to apply acoustic response to it. So that's where you would take that part of the model and move over to Actran. Again, which one should you use? Well, it depends on what you're looking for, and it is toward the end of this presentation. I'll go into some detail about, hopefully give you some idea of which one you might want to pick. Okay, so to start off, we'll do kind of a static versus random analysis, more for someone who's kind of new to this. Perhaps you only do it every once in a while, and then we'll take a little bit deeper dive towards the end. So just to make this comparison, when you're working on setting up a model to do random analysis, it's fairly complex. There's a number of different things you need to take into account. I would say that you can take a very conservative stab at doing random analysis and get there very quickly, particularly using something like MSC.Random. That's pretty easy to do. So I want to make some comparisons of what you're at least looking for. When you're on the fence, if you will, whether or not you need to do random analysis, it is possible to go ahead and say, well, I don't have to actually do random analysis. What I can do is just apply 100G load or some other load factor that someone has worked out, or maybe perhaps you worked out some time ago, and say, well, if I just apply in static analysis an inertial load of 100Gs and X, Y, and Z, and take a look at the structure that way, that's a good representation of what my random loading environment is, and that'll cover me. My model is fine if it survives that. Perfectly valid. There's plenty of cases where the input is random, but you can get away with these types of assumptions. So that's fine, but particularly as we get into lightweighting, you're trying to make higher performance structures. Perhaps they're going into a little bit different environment than they originally designed for, or maybe based on the failure of the structure, you may find that, well, you really need to come back and take a look at it. So hopefully this presentation will help you out a little bit in thinking about that and setting up a model to do that type of analysis. So the little structure we'll talk about throughout actually the multiple pieces of software, and this is very general description here, is in this case a satellite where we have an electronics box, and then inside that box is a circuit board. And perhaps I'm the circuit board guy, and that's what I really care about, but I need to be able to understand where these loads are coming from and how this type of analysis is done. This electronics box could be also something that would be in military vehicle, off-road, automotive. Does do random analysis, although it's usually more specific to components, particularly with electronics and things like that. A lot more modules and sensors. This is more pertinent in those particular areas, unlike a lot of aerospace, let's say a rocket, where the entire structure, the loading, is going to be some sort of random analysis. So we'll talk from this particular structure. So if we take a look between static analysis and random analysis, and I apply 100G load, we can see that the displacements between these two models are very, very similar. Wherever we have something that's relatively thin, not well supported, we're going to see higher displacement. There's really no difference in that. But some of the locations will start to change. For instance, the top of our little electronics box, same exact model, but we're seeing a little bit different displacement there. We hop over and take a look at stresses. When we do random analysis, we can get a thing called RMS stress. We'll talk a little bit about that later on, give you a little more reality on that if you're unfamiliar with it. But you can get a single stress value from doing both static and random analysis, and then see what that looks like. Do MSC stress, look at principal directions. It's all the same type of information. We take a look at the model there. Same model, 100G static acceleration. Maybe it should be higher, maybe it should be lower. Again, we do see the same general trends as we looked at in the displacement, where we have our bolt holes for that circuit board. We do see higher stresses in the corners and at the center. But if we look a little bit closer, we're starting to see some differences of where the higher stresses are, not necessarily the very high loads for the connections, but the other general parts of the structure are starting to differ. So this is where our static analysis that we perform, it's pretty close. If we put on an appropriate amount of inertia load or G loading, but it's still not quite the same thing. And this is where when we get into particularly thin structures, we really need to think about doing a random analysis. So that's kind of drawing that, again, that analogy from static to random. We might be able to get away with static, but we should at least check random analysis from time to time. So another set of similarities here is that if taking our little electronics box example, made a very nice looking model, very, very rigid, so we're not going to see a lot of response, if you will, to the circuit board on the inside. That's great, but it's also extraordinarily heavy, also very complex. So the question would come up is, well, what about just a simple sheet body, sheet metal type of box, and we make use of that. Fortunately, with finite element analysis, making those kinds of changes, particularly if we do, let's say, a mid-surface on that more complex structure, it's actually really easy to go ahead and switch those over. So that's kind of what my scenario is, and we'll take a little bit of a look at that in the demo part of it. But when we try and compare those two different models, just like if I was going to do static analysis, I have one model, I have the other model, or another rendition of it. We would compare displacement and stresses. Those things would be relatively similar, particularly when we're looking at RMS displacement, RMS stresses. Where things start to differ a little bit is acceleration. You can get a RMS acceleration, not really the same meaning as in static analysis, but it does give you a lot of information about where things might be too thin or they're getting heavily loaded based on what their mass is and everything else. That's where we start to deviate a bit from this comparison of static to random. But fortunate accelerations you can think about are relatively, you understand what those are. So it's easy to convey from one model rendition to another one that, hey, look, this thinner box, yeah, it did improve things here because it's lighter weight, but because of the load through it or what it had to carry, it is experiencing higher accelerations in other sections. So you can very easily see what the differences are. So kind of model comparison between those two, again, what you can draw from static to random analysis. Looking at the accelerations, don't read too much into these values. When I did this model, in this case, we have our circuit board in there. That's kind of what I'm concentrating on. Something like this, pretty good sized box. I probably have a lot of other things in there, and they have fixed amount of mass. They may or may not help us from a rigidity standpoint, but just looking at the acceleration, looking at throughout the model, we can see that the very thin structure at the very top of it, the top deck of it, we're seeing a lot more acceleration, particularly where we would think at the center, whereas the machined out box has some supports in there, so we're not seeing as much acceleration. The circuit board, again, we're seeing some generally the same trends, but it's guiding us to where, well, we might want to do something more to reinforce that structure and reduce the accelerations. We can also, again, look at stress or displacement. Generally, you'd be looking at stress to make a comparison between these two, where maybe the low-cost sheet metal box is going to get us in trouble, or maybe we can do some modifications to that to get it to pass whatever criteria we're looking at. One of my last comparisons between static and random analysis. When you do static analysis, you can oftentimes end up in a global-local type of situation where perhaps because of mesh density or you may not actually even know exactly what some of these components are. It's not unusual to make a global model, be relatively big, probably a relatively coarse mesh, and then once we've solved that model to some sort of satisfaction, we would go ahead and take the, let's stick with the static analogy here, the forces and moments, and apply it to our substructure, in this case our electronics box, and then from that electronics box we would apply forces and moments at the points where it connects to the circuit board, and we might hand that over to the people or organization that's working on the circuit board, and we would think about passing the loads from one model to the other. Yeah, we might do that for the two general reasons I think of anyways, is that when we're originally designing the structure, we really don't even know what the budget is for that structure. We just know notionally roughly how much it's going to weigh and where it is. So that's one way to get around that problem and not have to wait for those individual components. The other big one, of course, is just model size. How long is it going to take to run? I'll hopefully briefly get to talk about this towards the end. Other schemes to get around the large model problem and give you a relatively, well, a very realistic representation of some components, of course, is using SuperElements. So SuperElements do come into play, and that might guide you which direction you go. Maybe not initially, but if you're doing design work, they can be very useful for speeding up your analysis. So that was mostly, from my perspective, what we talk about from a static analysis, doing global-local analysis. Random analysis is exactly the same. The random analysis that you do for the full structure, it's common to pass that on to the substructure. The difference is how we do that. We'll be passing off PSD, power spectral density results. It could be accelerations. It's pretty common, but it could be also other types of loads over this frequency range to say, well, this is what your loading is into a substructure. This is also where, again, this kind of global-local approach, the random analysis you do for probably the larger structure is passed on to subcomponents. Another analogy or thing to talk about here, again, this is all relatively general information, is that acoustic loads, we'll talk about that very briefly at the end with Actran. That can be a very large part of, or actually the entire load for something like a rocket. The full vehicle is subject to that. Components on the inside may or may not be being in housings and covers and things like that. For instance, our circuit board, it may not actually be subject to any acoustic loading at all. One of the advantages of this approach, global, local, or passing loads on from one model to the other, is that obviously someone needed to do the acoustic loading on the full vehicle, or you might have some test data from that. But once we resolve what those loads are at the points where the other part of the structure connects in, that external loading, the acoustic loading, is already a part of that load. So the guy who's working on the electronics box, if we are relatively certain that the acoustics is not really a factor inside the housing, inside the satellite, he doesn't have to worry about that. He's going to get all that information summed up at however the thing is connected to the rest of the structure. So that's generally how this works out, and where we may not have to think about acoustics, we would use only Nastran to do something like that. But there could be other effects in there that could be driving it, again, reverberation off of the walls and the housing that we'd start to think about, where we would go, hey, I happen to have Actran, why don't I give that a shot and apply that to this internal structure as well. Okay, so that's about as much analogy as I can draw from static versus random analysis. I'm going to give you a short overview of random analysis based off of actually other articles and things like that. I will go ahead and try and show this slide again at the end in our Q&A section. These are a number of webinars that you can find on SimCompanion. Particularly this first webinar, WM5, is from Mohammed Barbella, who wrote MSC.Random along with Jim Leadham. But I'm giving a presentation on it. The first part of it is talking about the comparison between the utilities random, which is the older version. If you're using that, I highly suggest you don't use it anymore. There's a number of advantages to the other tool I will show here in a few minutes. So he gives a comparison of that, but then he also walks through what is random analysis. Far better job than I will in my given amount of time here. Besides that article, random analysis with multiple inputs, that's something else actually, Mohan, that was covered in that first presentation, and that's a pretty common question that comes up. Element size, I might touch on that if we get time in this presentation. There's other aspects of doing random analysis I didn't get to, and I just time, but random analysis, the output from that could be used for fatigue analysis. So if that's important to you, that's another article on it, and I believe we have a webinar on that as well someplace. So it's a whole other aspect of, we go to the trouble, if you will, of setting up our model for doing random analysis, but we can also carry that over and do fatigue analysis as well. There's a few variations on that, and again, I'm not really going to do a good job at getting into all those different things. So these are a number of articles that are definitely worth your time to take a look at if you're either already doing this as a type of analysis or if you're contemplating it. Okay, so what we're going to talk about and what I'm going to demo is on the left-hand side, the MSC.Random. The way this works out before kind of get into the explanation of random is uses Actran. Actran creates just a frequency response analysis, so that's all it does, or that's all it actually sends out to Nastran. Then we come into the Actran MSC.Random module. We bring in that frequency response analysis, or frequency response results. We combine that with the PSD of what the loading is, and then we can look at XY plots. We can make fringe values from that. We'll do random results investigation once we bring those two things together. So that's the way MSC.Random works. There's two parts to it, if you will. There's two types of analysis that are done. One is the Nastran frequency response, and then the other is combining that with the PSD to get the random results for you. Nastran.Random is a little bit different. It's all done in one shot. It's a response, and then random is, for those who generally the way that this is termed is something more than a post-processing type of event, although it's can get fairly complex and there's lots of interesting things associated with that. But it's all done at once. But then the post-processing for that is usually FO6 file or XY plots. So those are kind of the two distinctions between MSC.Random and Nastran.Random, and here nor there, generally the MSC.Random is a little bit easier to latch onto, particularly for someone who's new, so I'll concentrate more on that. Let's see, so when we talk about random analysis, It's a very short overview. There's two classes of dynamic loading. There's a more deterministic type of loading. The top one on the left-hand side, acceleration versus time. Good examples there is car suspension going over a bump, aircraft landing, drop test, things like that. You can see, just looking at the results, where the peaks are. If we can actually skip the dynamic analysis all the way around and just stick with static analysis, that's possible if we can determine what those maximum loads are. And in part, that's where we can get away from even doing random analysis if we just apply very high G loading. So that's one way to go. That could work if the part, based on its utility or just, for whatever reason, the way it's designed, it has to be robust enough for other reasons that dynamics, even in a dynamic loading, are just not important. We can skip it. But as soon as we start making it light, I usually think of aircraft and things like that, light and floppy, well, then we have to go ahead and at least do some sort of either transient response, so over time we would apply this loading, or perhaps we'd even still look at this and go, well, I know what the frequency content is of this type of event, so I would actually do a frequency response instead. Where random analysis comes in is that when our environment it looks more like the lower plot, where it's not deterministic, we're not really sure what the magnitude is at any particular time. This is where we need to turn to doing random analysis. Satellite launches are really good. Basically, all their loads, really good example. All their loads are going to be assessed this way. Aircraft also has a large component of its analysis that is usually subject to this, but they of course have a lot of other loading that they've made that assessment that based on most events, it's going to be basically a static type of analysis. Transportation, again, most of the structure is not really, you don't really need to look at it from a frequency, from a random analysis perspective. They do usually, for noise, vibration, and harshness, have to do frequency response, transient response, but there are parts of the cars where you are doing a random analysis, but it's usually more for specific components for specific reasons. Okay, so another way to look at this is from data that we might get, so dBs for frequency. When we see something like this and we can't really characterize it, we can't necessarily say at a particular frequency what the input is. What we'll do is go ahead and turn that into more of a power type of input per frequency. And when we're looking at it from that perspective, it's statistical in nature, the results that we're going to get back. But what we will actually say is that 68% of the time, we should never go up to this value, be it displacement stresses or something like that. So this is getting into statistics, so we'll usually do some multiplications on top of that to say, well, 99% of the time we're not going to see values that are going to reach that high. So it doesn't necessarily capture the, if you will, very random, very large changes from the loading that you have recorded. There might be others that might spike it even higher, but it does give you a really good idea of what your overall stresses, displacements, accelerations, those are from doing analysis this way, but there's always a chance it could spike a little bit higher. Okay, so how is this different from frequency response analysis? Again, frequency response analysis, we actually know or have assumed that we know what the input is at a particular frequency. Random analysis, we don't. Or what we're really doing is kind of capturing what the overall input is, be it acceleration, which is more common the case, but it could be pressures or something like that. So we're capturing general perspective of what we've generally seen from loading over a frequency range. Oftentimes this comes from a number of different test cases that we've gone through. Nice analogy that they have, and actually the NASA 122 guide is talking about multiple airline flights. They're never quite the same. Same with rocket launches. They're not the same from one to another, but you can get a general sense, kind of put them all together and you can capture what the general loading is, or what the, in this case, we'll figure out what the power is. So it's usually power spectral density, so it's power per hertz that we're going to load into the structure. Fortunately, this went very well with my little electronics box example. Let's walk through satellite. This will be the global model, if you will, that will take a look at the satellite. My little electronics box would be the red brick area, but in this example, we're looking at the antenna up there at the top, and we'll want to see what the response is. So when we talk about doing a random analysis, again, there's two parts to it. There's frequency response, and then there's the post-processing step, which is doing the random analysis. So let's talk about frequency response here. We have our satellite. There's some sort of loading, usually a base-shaped loading that will apply at the bottom. When we do random analysis, what we're looking for is just a unit load, usually unit load acceleration, although this as well. And then if we think about what happens at the very top of the satellite, in this case maybe a little sensor that's up there, when we do frequency response and we have this unit acceleration, what we're looking for is what is the magnification of that load. In this case, what is the magnification of the acceleration up at some other point in the structure. We can get the acceleration anywhere we like on the structure, as long as it exists in, well, I'll ignore that conversation, but basically what it is at different parts of the structure. So when we take a look at these results, the tip acceleration results, the red line there, as we go up to, up into the, towards 100 hertz or so, it peaks up and then it'll actually reverse. Just to reverse in phase doesn't necessarily mean that we're, well, actually we'll decrease the acceleration, and then we'll go up to some peak, and then it drops back off at the higher frequency. One of the very common things with most structures we're around or some sort of size is that once they get up into the higher frequency range, the response is effectively deadened out. It's because the phase in the loading in there, or the response from the structure, basically there's becomes just a one unit acceleration. So there's usually a cutoff that how high we need to go with our frequency. In the previous plots, I won't go back to it, but we talked about the dB per hertz. Your microphone, accelerometers, however you're getting that type of data, may of course go up into much higher frequency range. That's great, but from a practical standpoint, when we do a frequency response analysis on a structure, part of what we're also getting, just looking at it without any idea what the load is, that we'll see at the higher frequencies, there's no real response. It just follows whatever the excitation is. So we do usually have a pretty good idea of what that range is. It's usually up to about 2,000 hertz or so, depending on what you're working on. Very, very big, very, very small. Of course, you could see some differences in that, what range you need to take a look at. Okay, so this is the frequency response part of it, and what we're usually getting, again, is what the output is at certain points, and what the, if you will, magnification factor is there. So how do we go from frequency response to random? Our PSD is some sort of quantity squared per hertz. It's usually g squared per hertz is usually what I'm used to seeing. We have our basic unit base acceleration, which in this case is a satellite, so we have 1g over the entire frequency range, and we're just using that basically as a function to understand other parts of the structure, what the magnification is. Then the other part that we have that we've had to figure out somehow or another is the PSD. So someone else usually figures this out, or described before in the global-local analogy, someone may hand this to you because of the analysis that they've done on some other probably larger part of the structure. So what do we actually do here when we talk about random is that we already know what the magnification is for the different parts of the model, and then we multiply it, and actually we square it, multiply it by what our input PSD is, and then we get some sort of magnification on that. So if we kind of look from the plot to plot, all that we've done, usually the input is much higher at a certain frequency range. I'm not going to get too much into that. You can see the input PSD goes up And then at higher frequencies, it drops back off again. So that's just a product of usually the way most of the structures work. And of course, that offsets what the loading is that we will see up at the satellite dish, up at that other, at the antenna part of it. So if we want to go and look at this and kind of quantify it, talked about accelerations being a good way to judge your model or maybe a comparison of models. So if I do this right, take a look at frequency response analysis. So I haven't done the random part. Over on the left-hand side, we look at 148 hertz. We can measure up to what that response is. We see that's 267, which turns into about 7G loading. So for a 1G base shape, about 148 hertz, we're going to see about 7G load increase, or if you will, loading up at the antenna. If we want to go farther and see what the output PSD is for that satellite, what that sensor is, again, whatever we figure out from this analysis might be passed on to perhaps the person working on the sensor up there. We can go ahead and figure out what it is at a particular frequency. So we can look at the response output, see 148 hertz. We see what the input is. Usually could be 1 or some percentage of whatever our input is. So in this case it's 55 or 0.55, and we multiply that by our G loading magnification, that gets our G squared per hertz. So if we want to look at a particular frequency, we can take a look at the results there, and if we go ahead and carry that through, we can go ahead and figure out what the output PSD is for the rest of that structure. Other part here, very practical aspect, is depending on how closely we calculate that output based on our what we found from the larger part of the structure, that is the output PSD, but also we can refine what that response is. This is where sometimes we are asked to go back and say, well, can you get a few more modes, take a look at certain sections in a little more detail, and sharpen up our pencils on what that, if you will, the input PSD will be to another part of the structure. So that's part of how we assess and how we pass this information on. A little more detail, talked about before, ways that we assess the information, at least the easy part of it, that is very comparable and very useful is when we look at RMS output. RMS is root mean squared. What it comes down to is when we looked at that other plot before, and this is what we would get from using MSC.Random. We could also get, of course, the same values from Nastran. It's basically the area underneath the curve. And that makes up what the input is. So this is where we will get our 1 sigma stresses, displacement, accelerations, and 1 sigma from a statistics standpoint, 68.3% probability we won't exceed that. That's okay, but we'd like to get a little bit better chances. So we'll go ahead and use 3 sigma, which is relatively common, and that gets us to 99.73%. That number varies. It could go up higher or lower, but do keep in mind that the output it's giving you by default is only a 1 sigma, so that's not all that great. You usually do want to go ahead and multiply these values in order to get a 3 sigma type of output, and you could do that either on the MSC.Random side, you could do it actually in Nastran with the output that's there, or you can also do it under regular Actran results. You might want to multiply it there, but do keep that in mind that you're usually looking at a 1 sigma by default. As far as what the outputs are, this is just from Actran's MSC.Random module. After we've done our frequency response, we acquired our PSD input, we can get stress, force, strains, accelerations, displacements, so we can get all these types of output. We do need to have requested those in the frequency response analysis, though, in order to get those final RMS output. But the nice thing, again, about these is they're a single value, a lot like doing static analysis, and so they're very easy to compare. So again, I will stick to the MSC.Random for a very short demo here. The Nastran is all done at one time, and that has both some, if you will, some advantages and some disadvantages we'll get to here in a second. So let me go ahead and step out of the presentation, and given our lack of time, I will just have to go through this very quickly. So Actran up here, we're going to kind of start at the end just so you can see what we get. when we do this analysis, again, we have to do a frequency response. It could be modal or direct. Hopefully I'll get to that at the end. Doesn't matter which one you use, but it does have to be a frequency response. We don't do this in the time domain or transient response. So we can see what these results are. Using MSC.Random, I actually do not need to bring the frequency response results into Actran. I completely leave them out. In this case, I did. So we can see that we're getting answers at different frequencies that were requested for the analysis. This is also to the point of sharpening our pencil. If we need to get higher fidelity results, maybe for the output PSD from, let's say, my box to my circuit board, I might have to ask for a lot more of these. Fortunately, they're relatively cheap, particularly with the modal solution, so it's not that big of a deal to do it. What I'm looking for, at least from a simple to compare, easy to look at, would be these RMS values. So MSC.Random module creates these for you. I gave them my names, and let me go ahead and pick one out there. So in this case, it's RMS stress. I did have to go ahead and label it. I can go ahead and look at what the MSC stress is. We'll get a little time to chat about that, but one of the very unique things about MSC.Random is it does make use of papers from originally San Diego National Labs. There's probably some other references out there as well on how you do random analysis, or how you get MSC stress from doing random analysis. It's not very straightforward. The way we do it is a very it's more precise way. It's not the general conservative method of just taking whatever the random results are in X, Y, and X and Y and the shear values, and combining them together as you normally would, which works, but it's a very conservative answer, probably where you would stick with a 1 sigma, but you'd still have some guesses or some questions in your mind where it's going to be better or worse. So MSC stress is an important aspect that you can get from MSC.Random. Other parts here is displacement, so RMS displacement. So this is actually just 1 sigma. I have it multiplied by 3. So 68% of the time my displacement should stay under this value. That does leave me a fair amount of chance that it will be higher than that. Acceleration. How I've loaded this model is actually using a base acceleration, so we can see what this value looks like, and this is going to be in inches per second squared. So if I want to look at what the actually I can do that here. If I want to know what the G's are at different parts of the structure, this is relatively common that we have to do something like this. Let's get out of that little guy. Those of you who are familiar with Actran, this is not a big deal, but I can take a look at my acceleration, and then we can do some sort of scaling on it. So if I want to know what it is in G's, okay. So we can see we're about 226 G's at the highest, actually at the edges of the circuit board. Probably not a good thing, but it's very easy for us to see what that is, and that's very easy to relate as well. So if perhaps that loading wasn't too bad, circuit board guys were okay with that, then they might actually just apply a static loading and be able to cover, although the acceleration is lower in other parts of the board. So in short, this is what I'm looking for from RMS output. So that's one of the things it gives me, a frequency response we can look at there as well. I guess the 2 cents on that is that if we want to look at stresses, displacements, things like that from the frequency response, we can do that. But when we do the assessment, who's worse, we have to look over the entire frequency range. Again, possible, but looking at the overall model, overall comparison, that's a little bit more work. Okay, so how did I get here? If we want to go ahead and make use of MSC.Random, we'd go up to Tools and Random Analysis. So I have that one up here on the side. The other way I'm actually telling you not to go, one would say this doesn't work, well, it does work, is under Applications, Tools. So under Utilities Applications is MSC.Random. Those of you who have used this before in the past, you could actually be using it now. That's fine if it works for you, but you can't do the MSC stress, can't take very large results files. The general notion is just don't use it. Unfortunately, we aren't good about pulling things out of the utilities menu. There might be someone making use of it in a way that we don't understand, so we have a tendency to leave everything in there. But we highly suggest you make use of the Tools Random Analysis. Okay. There's a couple of different ways that this can go. The MSC.Random tool will allow you to or help you actually set up the model and do the frequency response. The actual random analysis, there's XY plots and there's RMS analysis. So when we're actually doing random analysis, XY plots and RMS analysis, if we just want to set up the frequency response, we do have an option there as well. I don't normally go this way. I would say anyone who's done this a fair amount, they don't go this way either. It will effectively set up a solution 111. It is intended for a base shake. I would pick a number of nodes and say these are the nodes I'd like to excite in the Z direction. We combine this in with our constraints and we say what our frequency range of interest is. We can also define things like damping. My settings here are kind of wiped out, but we can say what the modal damping is, and it might not let me go. Doesn't get applied. There you go. Okay. We can also say what our output frequencies are. So those of you who have set up frequency response analysis in Actran, it's basically the same forms. We've just moved them over to MSC.Random. So if you're experienced, generally you'll set up your model, you'll run your frequency response under, if you will, regular analysis. You probably won't come to random. If you're relatively new to random analysis, you don't do it very often. Actually, this is pretty good. It's a nice, easy way to set it up and at least try something out. Once you set up the analysis part of it, I've already done this, so we won't necessarily the message that comes up. Then we do have to go ahead and run the analysis. The module itself will not do that for you. So after we hit apply on that, we go to analysis, which should be up here on the side someplace. And that will actually set up a job for us, and it will, interestingly enough, have some direct text input, param and force motion, whether or not it's absolute or relative. Won't worry about explaining that, but it sets up a number of things for you. Some of them are under direct text input, but generally it's just a job setup. So we run our analysis. Again, this is just the frequency response part of it. We do have to make sure that that runs, which is again another argument that you should be probably running this, run linear static, normal modes, do the other analysis first. Before you hop over to doing random, but here or there you could do it different ways. So the other important part of it, which is the actual random analysis calculation, is we pick what our XDB is, pick our input PSD, which I haven't actually showed you where we set that up at. So we input PSD, we give it some scale factors. Sorry, actually the first part was setting up what the results are, which ones are we going to use. And then we can go ahead and have it calculate something for us. I'll pick acceleration is usually what I want, and we're base shaking it in the Z direction, so it's dock 3, and where I loaded this was actually on the arms here, how we grab onto it. And let me see if I can get things to cooperate for me. And they are not. Let's see here. There it goes. So on that one, what am I doing something wrong? There you go. All I was looking for is the base node on the edge that I picked is the guy in green. So that is the input PSD is what we're seeing. We are looking at accelerations. So accelerations actually come up to 1. But most of the time they're about 0.1 or so over most of the frequency range. Something like that from input PSD, relatively common. The other point I picked was on the circuit board post, and so we see some sort of magnification there. Fortunately for us, that magnification doesn't happen until much later in the frequency range, so that's a good thing. Now that's a perspective of very heavy box, very stiff. Maybe things just work out this way. If I were to look at the thinner box, we'll see a lot more response, and so it might actually push the wiggly lines, if you will, farther into lower frequency range, and that would be very bad, and we'd have to really think about that. So generally this XY plot is what you look at to investigate your model. Let me get rid of that. And then we can go under RMS analysis, and then same thing, we select our XDB and PSD, I've already picked it, and then we have our output available here. Again, various output is only available if you requested it inside the frequency response analysis. I missed a few. So we hit apply on that, and then it would actually make those results under results, and we can go take a look at them. the interest of time, I really can't do much more than that for this explanation. One of the things that's very nice about random, touch on in the thing here, is that we have an opportunity to experiment quite a bit, whereas when we do random analysis and when we do Nastran random analysis, we have to run each one. If I want to try a different input PSD, I have to run the entire analysis again. There might be some ways to get around that, but generally that's how it's going to be done. In this case, I could have, and when you do random analysis, you will have loadings in different directions. You might have several XPBs. You might also have several different input PSDs that you want to take a look at as well. They could be for different scenarios, and with random, MSC.Random, it's very easy to go ahead and pick those off and try those out. You can also do some slight scale factors and things like that. That input PSD is something that we create under fields. One quick word on that. So this is my input for this particular model. Nice bit here is that we can do import and export of CSV files. So we can go ahead and make a record of that input PSD. Bring that back into maybe another model. This is also a way to consider if you're getting your results from someone else or some other type of program, we can ask for that and make it easy to get that data in. Usually they're not very difficult to look at and type in, but it is nice to keep a record of them. And then we just do our regular analysis. Okay, again, interest of time, which I've already got myself well behind, I'm going to hop back over to the presentation and bring up a couple of these key points. So as Christian brought up, when we do frequency response analysis, there's a number of other things that happen first. You should have done just regular linear static, normal modes. Even if you're doing direct frequency response, you want to know what the natural frequencies are. It's going to guide you in your mesh size and also gives you a sense of, well, if there's any problems with the model. And then frequency response is another aspect of it, and then frequency response with the input PSD or our loads allows us to do a random analysis, and that may be daisy chained together. Okay. One of the ones I wanted to get to here, so I stuck it up front, was contact is obviously being used a lot more body to body. There's three different types. There's permanent glue, there's nonlinear glue, which is where it actually changes based on load. That can also be used if we want to do breaking type of relationships, things start to fracture. And then there's touch, which is arguably, most people think about contact, but that's what they think about as heel-toe type of effects. The only one that's actually pertinent for doing random analysis or any type of linear dynamic analysis at all is permanent glue. So before the analysis starts to run, before load is applied, we'll go ahead and glue the thing together or glue together different parts, and that'll be basically used for assembly. I won't judge, but there's a way to do, let's say, touch analysis. There's NLROPM, and we can write out what the contact representation is as MPCs. So we write out the Lagrangian multipliers for that. Basically, it's a snapshot of what that contact relationship looks like. It's only good for that load, but you can go ahead and take those MPCs, and then you could run these other analysis with that representation. Generally, I don't think about it being when I've seen this type of work done, and I think it might be valid, is not when something is fully broken or falling apart. It's usually where you have bolts involved, and for most of the time, it's one side of it is touching and the other side is not. That's where this type of method where we can get the MPCs is probably pretty valid, and it's a good way to assess it. But it's sinusoidal type of reaction that your structure is seeing under frequency response. So be very careful about this, but you can make those types of assumptions and store the contact as MPCs. Random analysis in Nastran. Again, this is a traditional approach. It existed before MSC.Random. You can use both direct frequency response or modal frequency response. MSC.Random, I'd actually have to think about that. It only writes solution 111 or modal frequency response, but it probably doesn't matter what you use for an input. If you want to get some more information on this dynamic users guide, SimCompanion are good places to look for more information, particularly the dynamic analysis users guide for theory part of it. This is not generated within Actran, but the input deck board is actually really simple. Below I have it highlighted in red what you would add to an input deck. So there isn't actually a whole lot there. Output, though, is limited to FO6 file, or you can make XY plots, and I'll have 2 cents on that. So these are kind of the overall tips for Nastran.Random, what you what you can do with it. It's again very similar to MSC.Random, but a little bit harder to work with. XY plots is one of the main output. The better place to look for advice on how to set up XY plots, well, actually the best advice is to find similar examples in like the Dynamic User's Guide or maybe from SimCompanion. But the SuperElement User's Guide actually has some nice advice on how to do XY plots, even if you aren't doing SuperElements per se. When we take a look at this type of information, we can actually turn the XY plot, which is a PostScript, into some sort of image or PDF file or something like that, or we could actually print it. But more times than not, what we're actually looking at is the FO6 file. You get a very nice summary. In fact, you can do XY plot where it's just a summary, and we can get these values out. These may be meaningful to you as they are, or you might just copy-paste them into Excel and make your own plots. There's a couple of different ways around that. But usually, again, Nastran.Random, this is how we're actually looking at the output part of it. The other part of the output that you get that you can look at in Actran would just be the frequency response aspect of it. One of the questions that came up, which I didn't think about it much of the time, but actually is very, very useful, is that can we run Nastran.Random, can we have external SuperElements, and can we recover results from within the SuperElements themselves? Setting up the scenario for this is difficult to explain. If we talk about our little airplane model down there, let's say the cabin is something that we're redesigning, so we would leave that in a residual. We'd have the rest of the parts be SuperElements or external SuperElements. External SuperElements, we can do the calculation, get what their stiffness, their masses. We are working the dynamics area, so we do need to do a component modal synthesis to make an accurate representation of the dynamics at where these things connected together. A lot to say. This is where we will have the SuperElement User's Guide. But the key part is that we can keep iterating on the fuselage. It will run much faster because the rest of the structure is external SuperElements. But I can go ahead and say, well, continue to give me RMS stress on some part of the structure someplace else and let me see what the effect is. So that knowledge base made a very simple model and outlined that, yes, it's possible to do that. None of the guides, nothing ever has said that that's not possible. Just want to make sure it was, and it does work out. And again, you could get benefits from it for a particularly large model. Other points here on Nastran.Random. Nastran.Random can be used with design optimizations that might keep you in that solution. MSC.Random cannot. It's a separate way that it's there to go ahead and calculate the random response. So that's a good reason to stick with it. It doesn't necessarily mean that you might not actually start your model in MSC.Random, doing random analysis there, making sure everything's right, general comparison, and then you might convert that over to Nastran.Random. Again, the input cards in Nastran for random are actually relatively simple. EC stress is a pretty notable, important aspect of MSC.Random. Again, it's a not super conservative type of calculation, and it is worth keeping in mind. At least reduces some doubt in your mind about what you're looking at when you're using those methods. Unfortunately, Nastran.Random doesn't have that capability. We do have an open request for that. It didn't make 2016, so we may see that in the future. Nastran.Random, as far as the output, RMS, things like that, there is a number of elements that it doesn't support. It won't give you information. C-Weld, C-Fast is one example. Talked a little about contact before. Contact would just be a frozen state. It still is worthy of making use of it, though. From an acoustics perspective, there's interior acoustics that could be used to some degree with Nastran.Random, but the exterior acoustics is by no stretch of the imagination a replacement for Actran. It's really just for assessing what the external responses are, what the decibel levels would be from a structure. So that's Nastran.Random. MSC.Random talked a little about already, relatively easy to use, lots of different output quantities, including von Mises stress, again, easier to experiment with. It has been improved using the 100 tools. It can handle very large XDB files, also different output requests that you may have made in there. So it works out very well. Please do make use of the 100 tools. Do not make use of the 100 utilities. Okay. Actran was acquired by MSC some time ago. There are Actran application engineers. I definitely would be a neophyte in talking about or working with Actran. There's a number of notable webinars I found very, very useful to get my feet wet and to give me some explanation, as well as a little bit of a live demo type of scenarios. I'm going through some different examples, particularly for aerospace. That top one, spacecraft launch, exterior and interior noise. That's a good presentation. Gives you a lot of idea of what you can do with it. Other presentations here I also found useful, and you might want to take a look at those. When Actran is run, generally the way this works is the structural part of it, it could be just the normal modes, natural frequencies are calculated by some other solver. It could be Nastran, it could be something else. And that's brought into Actran, and then in this case the acoustics are applied, and then we can get various output from there. The key part is that Actran can accept natural frequencies. It can actually calculate natural frequencies for you, is that specialized representations of things like fasteners, glue. There may be some other interesting elements. SuperElements would be a good example as well. You already have that information in the modes that you've extracted, and so you're passing it off to Actran. So it makes the support of elements on the Actran side a little bit less of an issue. One of the concerns I had, interest of time here, so this is generally how it works, is that there was a very nice workshop on doing random analysis inside of Actran. The example actually follows that circuit board or circuit board structure shown earlier, is that what it actually makes use of in this workshop is solid elements for the structure, and then 2D elements for the excitation for the interior and exterior acoustics. The entire model, it could have been shell elements. They do actually support a large number of Nastran elements. But if you do specialized things where they are making use of the modes from Nastran, it actually reduces their need or your dependence on what those elements are. So that works out very well. In this case, again, it was only doing a solution 103 normal modes, and then Actran would actually do the response calculation and the random. And in their interface, you can get out XY plots, von Mises stress, things very similar to MSC.Random, but there are some differences. Again, they have dedicated application engineers, very, very sharp people. Would want to talk to them if you need to get some more information on it. I just want to make sure from an overall random analysis perspective to make sure and bring that up. In the interest of time here, looking at MSC.Random or Nastran.Random correlation matrix, what the input is, you have to define where it is, whereas the big advantage here with Actran is that it's software defined. They can go ahead and say what the environment is, and they have a number of methods for both acoustics and aero type of excitation. That would be the loading into the rest of your structure. So lots of good stuff there. I'll go and leave this up on the screen. Again, these are SimCompanion articles that I would highly suggest you take a look at. A lot of good information there.